So if I want to compute the angular momentum of the system about O, then I compute the angular momentum about the center of mass and then the angular momentum of the center of mass about O. And whether it's a O here or a O there or a O here, angular momentum about any point on the ground will be the same, because the perpendicular distance this h is the same from the center of mass to this point, right? It's only this perpendicular distance which is like the arm of the angular momentum, right? So angular momentum about the, suppose this is the x direction, this is the y direction, then coming out of the plane would be the z direction, right, which will be the k direction. Into the plane would be the minus k direction. Now angular momentum about the center of mass of this is going to be mv into l, and it goes into the plane of the board in the minus k direction, and this about the center of mass again mv into l going into the plane of the board, so in the minus k direction. So about the center of mass it's mvl plus mvl in the minus k direction. Yes or no? I hope all of you realize this, right? So about the center of mass it's like 2 mvl in the minus k direction plus this is this is angular momentum about O. So this is angular momentum about the center of mass plus angular momentum of the center of mass about O is going to be 2m concentrated here into v into h 2m. The velocity of the center of mass is the same as the velocity of the trolley, it's fixed at this point. So 2m into v into h, that's the angular momentum of the center of mass about this point. So 2mvh, and again this v, this goes into the plane of the board, right? This goes into the plane of, that is again minus k direction. So plus 2mvh, and that digs in the minus k direction. So this is like a 2mv into L plus h in the minus k direction. That's the angular momentum about any point on the ground. That's the angular momentum about any point on the ground. Clear? There is a ring This is a smooth ring of mass m and radius r. At the point P, it's pulled with a constant acceleration a. You want to find the angular acceleration of the ring at this position. You want to find the angular acceleration of the ring at this position. Okay. Now, we look at the motion of the ring in a frame attached to P. P has an acceleration a to the right. So, the frame attached to P is a non-inertial frame, So, if I look at the ring in the perspective of the frame attached to P, then that's a non-inertial frame. So, then in a non-inertial frame, I would have to accommodate a pseudo force on the system. The pseudo force on this would be like a minus ma, which would be ma backwards. Ma backwards? Yes or no? Are you there with me on this? Now, since P is the point, about P is a reference point, I can take torque about this point, because this point is like at rest with respect to the ring. The ring, right? At this instant, this is at rest with respect to the ring. So, I am allowed to take torque about P. I am allowed to take torque about P because P is my frame of reference. It's at rest. It's at rest. Right? Its acceleration is 0 with respect to P. So, if I take torque about P, which is like a pseudo torque, so to say, loosely speaking, a pseudo torque because of the pseudo force, then that's going to be ma into r. Ma into r clockwise. Ma into r is the clockwise torque. Ma into r is the clockwise torque about point P. Right? This is torque about point P. Divided by I about P. I about P is mr squared plus mr squared, that's 2mr squared, that's 2mr squared, right? If I'm taking torque about P, I'll have to take I about P, which is like a 2mr squared. Then that will give me the angular acceleration with respect to this frame. Hey, but it's the same. Angular acceleration will be the same with respect to a translating frame or with respect to a stationary frame. Angular acceleration is going to be the same. Angular acceleration is going to be the same. So the angular acceleration is this. A by 2r. A by 2r will be the angular acceleration. Now, one thing, just in case, you're a little baffled with my liberty to apply torque about P and take torque equal to I alpha about P. I'll give you a regular situation in which I'll apply this torque about P, and that will kind of set you to think that I'm not cheating you here. Okay. See, what I did here was, all that I did was, I chose P as my reference frame, non-inertial frame. So I plugged in a pseudo force Ma, I took the torque about P. There was no friction, so there was no torque because of frictional forces. Ma into R, that equals I alpha, I about P into angular acceleration alpha. Deformation of the spring means maximum deformation. That's what is meant. So in this case, the spring originally in its natural state. Under the influence of this impulse V0, the spring tilts. The ends of the spring develop velocities, different velocities along the length of the spring. Difference in velocities along the length of the spring in due course will cause elongation of the spring, The spring elongates, continues to elongate such that the relative velocities of the two masses along the spring will become zero at some point of time. At some point of time, the relative velocities of the two masses along the length of the spring will become zero. After that, the spring will not elongate any further. When the relative velocities of the two masses, relative to each other that is, become zero along the length of the spring, then the spring will not elongate. The spring is elongating only because the two masses have a relative velocity along the length of the spring which is non-zero. Yes or no? So after a while, in a state of maximum deformation, which would happen, let's say, when the spring tilts by a certain amount, in a state of maximum deformation, the velocity of m1 with respect to m2 would be perpendicular to the spring. The spring will not elongate any further. You know what I'm saying? When the relative velocity of m1 finally again becomes perpendicular to the length of the spring, m1 with respect to m2 will become perpendicular to the spring. That means the relative velocity of the two masses has no component along the length of the spring. The spring will then cease to elongate and would have then reached a state of largest elongation. So just put the spring vertical, although it would have been inclined, but for the sake of representation of the velocity, let's say eventually in a state of maximum elongation, when the spring becomes, let's say, of length L0 plus x max, the relative velocities of the two masses with respect to each other, that is, will be like a VREL like this, Yes or no? Now, which means essentially relative velocities would have become perpendicular to the length of the spring. Spring will not elongate any further because the relative velocities will have no component along the length of the spring to cause it to elongate further. Now, in the center of mass frame, let's analyze this system in the center of mass frame. This is the conceptual notion, the physical notion. In order that the system migrates from its natural length to a state of maximum elongation. Physically, this must happen. Are you all okay with this idea first? Okay. Now, if I look at it in the center of mass frame, Now, in the center of mass frame, realize that the velocity of the center of mass here is what? V0 by 2, m1 V0 by m1 plus m2. m1 and m2 are equal, so velocity of the center of mass is v naught by 2. So the velocity in the center of mass frame, the velocity of this will be v naught by 2 to the right initially, because right, v naught minus v naught by 2. So that's for m1, it's v naught by 2 to the right. For m2, again, it has to be v naught by 2 to the left. Why? Zero linear momentum in the center of mass frame. m1 and m2 are equal, so m1 v naught by 2 must be equal to m2 v naught by 2. No net linear momentum, right? Now, finally, when this happens, again in the center of mass frame, no component of relative velocity along the spring. So all the relative velocity of the two masses is perpendicular to the spring, which means essentially something like this happens. Let's say at that state, v is the velocity of this mass in the center of mass frame to the right, and v is the velocity of this mass in the center of mass frame to the left. Right, so that the relative velocity is of these two masses with respect to each other is 2v, which is perpendicular to the length of the spring, causing the spring to elongate no further, right? That's this measured in the center of mass frame, everything in the center of mass frame now. And this length is like a L naught plus x max. Now, between these two states, can I not conserve angular momentum about the center of mass? The only force is the spring force. It passes through the center of mass, produces no torque about the center of mass. So, in the center of mass frame, I can preserve the angular momentum about the center of mass. Angular momentum about the center of mass, yes or no? Yes, right? So, only just to maintain consistency, let me just call it v by 2 and v by 2, so that there is like symbolic consistency. Then v becomes the relative velocity. V becomes the relative velocity of one with respect to the other, and v by 2 and v by 2 are velocities in the center of mass of the two masses perpendicular to the line joining them. Clear? Now, in this case, the velocity of m1 with respect to m2 is v naught. The position vector of m1 with respect to m2 has magnitude equal to L naught, right? So the angular momentum about the center of mass is going to be the reduced mass mu of m1 and m2 into relative velocity cross r12 cross v12, but r12 and v12 are perpendicular to each other. So the magnitude of the angular momentum would be magnitude of r12 into magnitude of v12, velocity of one with respect to. So r12 is simply this length, L naught, and v12 is like v naught. Velocity of this with respect to this is v naught. That's the angular momentum about the center of mass in the center of mass frame initially. Are you there with me? Finally, the angular momentum in the center of mass frame about the center of mass is mu into L naught plus x max into v naught, right? Relative velocity of this with respect to this is v naught. See, again in this case, relative velocity is v, which is perpendicular to r12, which is L naught plus. Yes or no? I'm sorry, v. Right? So that's as far as angular momentum is concerned, right? Now we have another principle in place. The principle is, I can apply work energy theorem in the center of mass frame. I can apply work energy theorem in the center of mass frame. Yes or no? Now, the only force is the spring force. Work done by the spring force would be negative of the change in elastic potential energy. Elastic potential energy is 0 here. Elastic potential energy is half K x max here. Right? Yes or no? Right? So, negative of the change in elastic potential energy, that's the work done by the spring force, which is minus half K x max squared minus half K x max squared, and that must be change in kinetic energy with respect to the center of mass. That must be change in kinetic energy with respect to the center of mass. Yes or no? Right? That means final kinetic energy half mu into v squared, because v is the relative velocity here, minus half mu v naught squared. V naught is the relative velocity here, right? Kinetic energy in the center of mass frame is half mu into relative velocity squared. So that's like a half mu into v squared minus v naught squared. Yes or no? Right? These are the two relevant principles. These are the two relevant principles. Now we just need to quickly solve. Minus half K x max squared is half mu into, if I took like a v naught squared common, then this is like a v by v naught whole squared minus 1 right? V by v naught is L naught by L naught plus x max. Minus 1 if I took L naught common from this, then that L naught squared and this L naught squared would get cancelled. I'm then left with 1 plus x max by L naught whole to the power minus 2 minus 1, right? And it's given that x max is small compared to L naught. It's given that x max is small compared to L naught. So 1 plus t to the power n, where t is numerically much less than 1, is approximately 1 plus nt, is approximately 1 plus nt. So this is approximately half of mu into v naught squared, and this one will get cancelled, 1 plus nt, you're left with minus 2 max by L naught. So then 1 x max will get cancelled with 1 x max, and then you'll be able to compute x max from these considerations, where mu is m1 m2 by m1 plus m2 and v naught is given to you. Clear? And you can just get a little more entrepreneurial. You can go back and solve this problem in the ground frame also and see what transpires, right? You can do that. You'll realize that the algebra there is a little more messier than the algebra that you encountered here. So there would be some merit in looking at this problem in the center of mass frame, which is what we did, right? A system of two particles m1 and m2 connected with an ideal spring is released from rest in gravity. If the initial velocities of the particles are v1 and v2 as shown, Find the change in angular momentum of the system relative to the center of mass and about the center of mass. Hey, this was the center of mass. Then it's like m1 plus m2 into g passes through the center of mass in a uniform gravitational field. The way it will make its passage through the center of mass, right? That means, what's the torque about the center of mass? Zero. Torque about the center of mass is zero. If the torque about the center of mass is zero, that means angular momentum about the center of mass must be constant. Conservation of angular momentum. If the angular momentum about the center of mass is constant, means change in angular momentum is zero. Change in angular momentum is zero. Right? Are you there with me on this? Now, the only external force acting on the system is m1 plus m2 into g. So, this is the only one that's producing change in linear momentum. That's the only one producing change in linear momentum. And change in linear momentum for a constant force would be force into the time over which it acts. That's the change in linear momentum, right? So, the change in linear momentum is m1 plus m2 into g into time t. That's the change in linear momentum of the system. Clear? Make sense? Alright, so we have this rod resting on a horizontal smooth surface and the point P is given a constant acceleration a to the right. Obviously, this rod would tilt this way. You would expect the rod to tilt this way. After a while, the rod becomes like this. Now, we will solve the problem in a frame of reference attached to the rod. In a frame of reference attached to the rod. It's in a vertical plane or a horizontal plane? Okay, so that's a vertical plane. That's a vertical plane. So that's mg. Alright. So then, this is the center of mass. This is the center of mass. Then with respect to this, with respect to the vertical, mg is like this, right? And there is a pseudo force acting on it, which would be ma like this, pseudo force which is ma like this. The angle that it makes with the vertical, let's say, is theta with respect to this, right? Now, about P, I can take the torque. I can take torque about P as long as I include the pseudo force. I am eligible to take torque about P. Torque about P would be I about P into alpha, right? What's the net torque about P? The net torque about P would be torque because of the pseudo force with torque because of mg. Now, let's say it develops an angular speed omega, a function of theta. Clear? This length is L by 2, half the length. L by 2. Now, torque because of ma is like ma into this length clockwise. Torque about P because of ma would be ma into this length clockwise. So, that's like ma into this length is L by 2 cos theta. This length is L by 2 cos theta. Right? Torque because of mg about P. Line of action of mg is this. The moment arm of mg is this. That is this length. So, torque because of mg would be mg into this length anti-clockwise, but this length is L by 2 sine theta. So minus mg into L by 2 sine theta. That's a net clockwise torque about P in a frame of reference attached to P. In a frame of reference attached to P. That must be I about P into angular acceleration. I about P. I about P is 1/3 ml squared. I about P is 1/3 ml squared into angular acceleration, which is d omega dt. Right? Now I need to find omega a function of theta. That means I need to dispense away t. I need to dispense away t. I need to bring in theta. So d omega dt, you would realize, is like a d omega d theta into d theta dt. But d theta dt is omega. D theta dt is omega. So this is like a omega d theta. Omega d theta, yes or no? So this omega d dt I can write as omega times d omega d theta. How about it? And then simple stuff, m gets cancelled. We have like a by 2 cos theta minus g or half, I can take common, a cos theta minus g sin theta is L by 3 omega d theta, right? So all that you need to do here is d theta here, d omega here. When theta is 0, integrate. When theta is 0, omega is 0. It starts with 0 angular velocity. When theta is theta, omega is some omega. Integrate both sides with limits of theta being 0 to theta, limits of omega being 0 to omega. You will get omega as a function of theta. Plug in this theta here and integrate both sides with these limits. Theta 0 to theta, omega 0 to omega. You will get omega a function of theta. Is that all right? All right. This V could be resolved as V cos theta perpendicular to OP and V sin theta parallel to OP. Right? Now V cos theta is responsible for omega, isn't it? The perpendicular component is responsible for omega. So omega is like a V cos theta divided by the length OP, which is h by cos theta. Right? The length OP is h by cos theta. Right? So which is like V cos square theta by h. Let's see omega. Right? The alpha will be d omega dt. Alpha would be d omega dt, yes or no? Which should be V by h 2 cos theta minus sin theta d theta dt. That's angular acceleration. But what's d theta dt? Omega. D theta dt is omega. So you can plug in omega from 1 and you can get angular acceleration alpha. Clear? The angular momentum about O, is going to be mv into h, isn't it? mv into h will be the angular momentum and it would go into the plane of the board. So angular momentum is mvh into the plane of the board. which is a minus k. That's the angular momentum. Right? What else is required? Sorry? So what? So what? Now, why can't that happen? Why can't that happen? Constant? Huh? No, there is someone which is producing this, right? This V, after all, it must be coming from somewhere, isn't it? It must be coming from somewhere. Now, that source is not. Only the kinematics are known. The dynamics are not known. It must be coming from somewhere. Some force which is causing this motion is responsible for that, isn't it? So, torque again is known from this. Torque would be I alpha about this point, I about O. If the particle moves with an acceleration a from rest, from the angular position theta equal to 0 at any time t about O, find the angular velocity. Okay, that means if the acceleration is a, then v is at. You can write v as at. If you write v as at and then differentiate this, you will get alpha, right? Angular acceleration, angular momentum. So v as at, differentiate L with respect to t, you will get torque, you will get torque, and also angular momentum would be this into v is at, torque would be dl dt, torque would be dl dt, that will be the torque. 7 and 8 are the same, except that you got to replace v by at and differentiate. So you will have an extra term. When you differentiate this, you will have an extra term. So this is a guided missile. This is a guided missile. So while the rocket propels horizontally with a constant speed u, at every instant the missile maneuvers its direction so that it's pointing towards the rocket. Such is the trajectory of the missile, right? Intended to hit the rocket. At the initial instant, since the rocket is here, the missile has a velocity directed towards this. So it's something like this. The missile takes up a curvilinear trajectory. The missile takes up a curvilinear trajectory and hits the rocket at r. At any intermediate instant, let's say this is an intermediate instant, the velocity of the rocket, the velocity of the rocket would be tangential to the trajectory and velocity of the missile would be tangential to the trajectory and would be aiming towards the rocket, which is initially, which at this instant is here and heading with a velocity u horizontally. So from instant to instant, the direction of the rocket changes so that the velocity vector points towards the position of the velocity of the missile, points towards the position of the rocket, right? Now, this is an intermediate velocity. It makes an angle theta, with the horizontal. Now, theta continuously changes. Tan theta is the slope of the trajectory, it continuously changes. It's a variable theta situation. A is the position of the missile at this instant, B is the position of the rocket. Now, AB, the line joining A and B are variable instances of the missile and the rocket respectively. AB is R, the position of B as seen by A. AB is of magnitude R, where R will depend on theta. R will depend on theta. For different thetas, you will have different separations between A and B. R is the relative separation between A and B, right? At time t equal to 0, the relative separation is L, isn't it? Relative separation is L. At time t equal to tau, when the missile hits the rocket, the relative separation will become 0. That is that at this point, small r will become 0. At this juncture, small r is L. Small r is the relative separation between the guided missile and the rocket, right? Now, there is a rate of change of r with time. R is actually decreasing with time. R is actually decreasing with time. R decreases because of the relative velocity between A and B along AB. Relative velocity of A with respect to B along AB is causing R to change, yes or no? What is causing R to change? The relative velocity along AB. Relative velocity along AB, velocity of A as seen by B along AB is V minus U cos theta, yes or no? Velocity of A with respect to B along AB is velocity of A along AB minus velocity of B along AB. Velocity of B along AB is U cos theta, yes or no? So the relative velocity of A with respect to B is V minus U cos theta. Are you okay with this? Right? And this is responsible for rate of change of R with time, right? This is responsible for rate of change of R with time, yes or no? That means this must be magnitude of dr dt. This must be the rate of change of relative velocity along AB is rate of change of AB with time. Magnitude of rate of change of AB with time, yes or no? Right? But R is decreasing with time. So dr dt must be negative. Dr dt must be negative because R is decreasing with time. So mod dr dt would be minus dr dt. Mod dr dt must be minus dr dt. So far so good. So we have like a V minus, theta is not a constant, U and V are constants, theta changes. Dt, t runs from 0 to tau, tau is the time when they hit each other, is minus dr, r runs from L to 0, so which is L? R runs from L to 0, clear? Now, this is not enough, this is not enough, we need to actually compute tau. The point where they hit, right? They collide at R, by the time they reach R, their displacements in the x direction must be the same. The displacement of the rocket in the x direction is how much? U into tau must be equal to the displacement of the missile in the x direction. The missile in the x direction is like v cos theta into dt. Sum of all of this, t runs from 0 to tau. Yes or no? Is this not the displacement of the missile in the x direction in tau seconds? In a small time dt, v cos theta into dt is the displacement in the x direction, right? So total displacement in the x direction is sum of all of this, t runs from 0 to tau, t runs from 0 to tau. Is that okay? Now this equation tells me that integral cos theta dt 0 to tau is like a 0 tau by v, is like a 0 tau by v. Integral cos theta dt is u tau by v. Here v can come out, v is a constant, this is speed, u is this, and I can plug in cos theta dt as u tau by v into this. See, when I integrate this gives me what? V into tau minus u times integral cos theta dt, which is u tau by v, that means u squared tau by v, that's the left hand side of this. When integral cos theta dt is replaced by u tau by v, and that must be equal to L, that must be equal to L. So tau then becomes v into L by v squared minus u squared. Obviously v has to be greater than u, and in the event v becomes equal to u, then essentially this line will become an asymptote and the collision will take place at infinity. If v becomes equal to u, then the collision will actually theoretically never occur. Theoretically at infinity, but would actually never occur. And v is less than u, the missile will never hit the rocket. right? This angle AOP is alpha, which is L by R. The angle AOP, this is not exactly quarter of a circle, it's given to be less than pi r by 2. So alpha is less than 90 degrees, it's given in the problem, right? Now this chain, whose mass per unit length is lambda, uniform chain, mass per unit length m by L, rests here, connected with a string to the wall. I want to be able to find the tension in the thread. I want to be able to find the tension in the thread. Look, as far as this chain is concerned, there are three forces acting on it. There are three forces acting on this chain. Any given element of the chain, for example, you take, if you look at any given element from A to P, then on this element, there is mg acting downwards, mass weight of this element. There is a normal reaction. There is a normal reaction whose line of action will always pass through O. There is a normal reaction whose line of action will pass through O, right? And then there is weight acting, dm into g acting downwards, right? For every, so then three forces on this entire chain consolidated. There is three external forces. P, normal reaction at every point, the line of action of which passes through O, and then there is gravity acting vertically downwards, right? Under the influence of all these forces, element by element, the chain is in equilibrium. The chain is in equilibrium. Realize that it needs translational equilibrium as well as rotational equilibrium. The vertical components of the tension, the vertical components of the normal reaction will balance the weight. All the vertical components will balance the weight. Now, as far as the torque is concerned, rotational equilibrium means torque about any point must be zero. It's your choice, right? Rotational equilibrium means torque about any point acting on this assembly must be zero. Now, why would I not take torque about O? Because all the ends pass through O, so I will not have the headache of computing the torques because of the normal reaction. I will just have to take the torque because of T about O and torque because of these mass elements about O. They must add up to 0, right? These mass elements produce a clockwise torque about O, whereas this tension produces a anti-clockwise torque about O. So the anti-clockwise torque in magnitude must be equal to the clockwise torque in magnitude about O to guarantee rotational equilibrium. Are you okay with this? Now, let me choose an element here, locate that element by theta, and the span of that element by d theta, this is the span of that element, mass element, and then the weight of that element passes through this, right? The torque, because what's the weight of this element? First of all, the length of this element is r d theta, the one I have chosen over d theta, this is r d theta, right? The mass is going to be lambda r d theta, mass per unit length into g, that must be the weight of this element. Now the torque that this element produces about O would be this into this length. Is that okay? Into this length. Now this is theta, this angle is also theta. So this length is r sin theta, this length is r sin theta, yes or no? So this into r sin theta, that's the torque because of the weight of a small element of the chain. That's the torque about O, yes or no? The total torque about O because of these weight elements would be sum of all of these, where theta runs from 0 to alpha, theta runs from 0 to alpha to cover all elements. Theta runs from 0 to alpha. That's a net clockwise torque about O. Which must be equal to the torque about O produced by T, which is T into R. This is R. So T into R is the anti-clockwise torque about O. So the magnitude of the anti-clockwise torque equal to the magnitude of the clockwise torque, so that no net torque acts and rotational equilibrium takes place. So T into R is easy to integrate, lambda is m by L, etc. What's alpha? Alpha is L by R. As you can see, the angle that it subtends at the center. Does it make sense to all? So, problem 11, which is very straight actually, very straight. Alright, mg minus t is ma. And then there is torque about this point, which produces alpha in this. Torque about this point, anti-clockwise torque is T into R. That's I about O, which is a disk of mass 2m. So I about O is half of 2m into R squared into alpha. Right? And then acceleration of this point is the same as the acceleration of this. So this is A. So A must be R alpha. A must be R alpha. From this, obviously, you can eliminate A and solve for alpha. You can solve for alpha. Once you solve for alpha, the kinetic energy of the cylinder. So the omega of the cylinder after t seconds would be alpha t. Omega is omega naught plus alpha t, right? So once you know the omega, the kinetic energy of the cylinder would be half I omega squared, right? So required kinetic energy is going to be half of 2m into r squared into omega squared, right? Let's look at 12, right? Right, so there is a constant horizontal force F equal to mg acting, and there is a vertical force mg acting, and on the mass there is a tension T acting, right? So the mass goes from B to C under the influence of all these forces, right? By the time it reaches this point C, let's say it develops a tangential velocity V, So between B and C, can I not apply work energy theorem between B and C? Can I not apply work energy theorem between B and C? So work done by this force F is force into displacement of this point in the direction of this force. That is, if this length is L, then this is L sine theta. So work done by force F is going to be mg into L sine theta, right? That's the work done by F. Work done by mg would be minus mg into this length. Mg is acting downwards, displacement aligned with mg is opposite to mg, is dA, but this length is L minus L cos theta, as you can see. AB is L minus L cos theta, right? So work done by mg is minus mg L into 1 minus cos theta. Tension is not doing any work because tension at each instant is perpendicular to the displacement or the velocity, right? Because this is a circular trajectory. Tension is not doing any work in this case, right? So work done by tension is 0. So from B to C, this is the work done by various forces, and this must be equal to half mv squared change in kinetic energy. That's one thing. Now, at this point, it's after all negotiating a circular trajectory of radius b of radius r of radius l, right? So then there must be a centripetal force providing the required centripetal acceleration, right? So what's the centripetal force? What's providing the centripetal force? G minus mg cos theta minus f sin theta, right? Minus f sin theta, that's the required, that's what would provide the required centripetal force. T minus mg cos theta minus f sin theta. F sin theta is mg sin theta. This takes care of the centripetal force requirement, which is mv squared by L. Yes or no? But mv squared by L, as you can see, is 2 times mg L sin theta minus mg L into 1 minus cos theta by L. Yes or no? See? mv squared is 2 times this divided by L. That's mv squared by L. That's the right hand side. Clear? We then have tension T as L gets cancelled. T as mg into cos theta plus sin theta plus 2 times sin theta minus 1 minus cos theta. Yes or no? Right? That's T, which could be written as equal to 3 sin theta plus, and then there is a minus 1 also, cos theta minus 2. Right? That's T as a function of theta. That's T as a function of theta. Now what is it that we need? Find the maximum possible tension in the string. Find the maximum, that's part B of the problem. Find the maximum possible tension in the string. Now, D would be maximum when sin theta plus cos theta is maximum. When is sin theta plus cos theta maximum? When theta is 45 degrees. Sin theta plus cos theta is maximum when theta is 45 degrees. It could be written as root 2 sin theta plus pi by 4 or cos theta minus pi by 4. The maximum value occurs at theta equal to pi by 4. Yes or no? So then T max takes place at theta equal to pi by 4. T max when sin theta plus cos theta is a maximum when theta is pi by 4. And theta is pi by 4. Does it make sense to all of you? Now, maximum theta, that's part A of the problem. What's the maximum theta possible? Given all of this, what's the maximum theta possible? Now, look at this equation, right? Between B and C, we've applied work energy theorem. This equation is work energy theorem between B and C. When would the particle not get displaced any further? When it would have consumed all its velocity. When its velocity becomes 0, then theta would have become a theta max. Are you there with me on this? Right? If it has velocity like this, it will undergo further angular deflection, right? But if the velocity becomes 0 at this juncture, then it rises no further. Theta becomes theta max when V is 0, right? So come back to this equation, work energy perspective. This theta would be theta max when this V becomes 0. When V is 0, right? Which means sin theta equals 1 minus cos theta. Sin theta equals 1 minus cos theta, or sin theta plus cos theta equal to 1, and that can happen only when theta is 90 degrees. This can happen only when theta is 90 degrees. Yes or no? So the maximum angular deflection can be 90 degrees here, 90 degrees. Sin theta plus cos theta can be 1 only when theta is 90 degrees. That's the only possibility, right? So theta equal to 90 degrees is the maximum angular deflection that could occur. This is very simple actually. The kinetic energy of a particle moving in a circle of radius r depends on the distance covered s. So half mv square displacement along the circle, half mv square is as squared, right? That's the kinetic energy. So at any given instant of time, is v is the velocity, then there would be a centripetal force. There would be a centripetal force requirement, which would be mv squared by r, right? So centripetal force would be mv squared by r, which is like a 2a s squared by r, right? Right? Now there is also a tangential force which depends on the tangential acceleration. There is a tangential acceleration which is dv dt. Tangential acceleration would be dv dt, resulting in a tangential force. Yes or no? V is not constant here, V is varying. So if V is varying, that means the tangential velocity is varying, that means there is tangential acceleration, that means there is a tangential force also. Now as you can see, V here is like a root 2a s squared by m, 2a s squared by m, which is s root 2a by m, right? So then from this, can you not compute the tangential acceleration using dv dt? Once you compute the tangential acceleration, which is dv dt, then the net force is going to be ft squared plus fc squared, ft squared plus ft squared. Clear? So we select the axis along the x direction and the y direction. There is a projectile which is fired along this inclined plane at an angle theta, same as the angle of the plane, with a velocity v, and with respect to the x-axis, this is the highest point. This is the highest point with respect to the inclined plane that it reaches, and when it reaches this point, the Vy becomes 0 at this point, and Vx is Vx at this point, right? Vy becomes 0, that's the highest point. It can go no further in the y direction. Now, that means the time taken to reach this point, let's say if that's t seconds, then in t seconds the vertical component of the velocity becomes 0. Now, vertical velocity in t seconds is initial vertical velocity, which is like v sin theta, plus acceleration in the y direction, which is g cos theta, so negative y direction, so minus g cos theta into t. This will give me the time it takes to reach the highest point. So the time it takes to reach the highest point is like a v sin theta by g cos theta. V tan theta by g is the time it takes to reach the highest point. Now in this time, it develops a horizontal velocity Vx, velocity in the x direction. So the velocity developed in the x direction and this up to this instant of time is initial velocity in the x direction, which is like a v cos theta, plus acceleration in the x direction, which is minus g sin theta, into time t. Time t is v tan theta by g. Right? So this is like a v cos square theta minus sin square theta, that is cos 2 theta by cos theta, right? Cos square theta minus sin square theta, cos 2 theta by cos theta, that's the horizontal velocity developed, right? Now realize that at the highest point, this is the highest point. It has a tangential velocity Vx at this point, which is along the tangent to the path, This is the normal direction. Realize this is the normal direction. That is the y direction in this case is the normal direction. In this direction, the acceleration, that is the normal acceleration, is like a g cos theta. And at this point, it's g cos theta that provides the required centripetal force. So at this juncture, if r is the radius of curvature, if O is the center of curvature, if r is the radius of curvature at this point, then the centripetal acceleration is like a Vx squared by r, that's the centripetal acceleration. And who provides the centripetal acceleration? G cos theta provides the centripetal acceleration. So Vx you know, and therefore the radius of curvature at this point can be obtained with this. Does it make sense to you? Right? Can I write this off? Right? In this case, when this prism is rotated with an angular velocity about this point, then mg moves in a circle of radius r, middle, means this is h by 2, right? So this moves in a circle of radius r, which is h by 2 cot theta. R is h by 2 cot theta, as you can see. So this moves in a circle of radius r, which is h by 2 cot theta. Now, who provides this, provides the centripetal force to this? This is moving in a circle of radius r with angular speed, synonymous with the angular speed of this, right? So it has a centripetal force requirement directed in this direction equal to m omega squared r. It requires m omega squared r. That is its requirement. And who fulfills this requirement? N sin theta. N sin theta is instrumental in accounting for this. And then what does n cos theta do? It balances weight, right? N cos theta balances weight. So you divide this by this and put r equal to h by 2 cot theta, etc. Fair enough? Make sense? Huh? Alright. So we have this cable moving upwards with an acceleration a naught, and then there is a string connecting it to the ceiling of the cable, and this particle is taken to a position. So I said this string makes an angle theta with the vertical. Find the tension in the string when the string becomes vertical. That means in this position, when the string becomes this way, find the tension in the string. Alright, now one thing for sure, we can look at this problem in the frame of reference attached to the cable, right? So when we do that, essentially we'll add a MA naught like this, so the net force acting on it in this direction is like a mg plus a naught, mg plus a naught, clear? Now, from A to B, let's say the gain in velocity with respect to the cabin is v. The gain in velocity with respect to the cabin is v. It's going to be horizontal, as you can see. I can apply work energy theorem. There are forces acting tension and m into g plus a. These are the only two forces acting, right? So with respect to the cabin, the work done by the real and pseudo forces mg and ma naught is going to be mg plus ma naught into this length. That's going to be the work done by gravity and the pseudo force. Force in this direction, real plus pseudo, into this displacement in the direction of the force. That will give me the work done mg L into 1 minus cos theta is the loss of height. This is L cos theta, L minus L cos theta, and this must be equal to, from work energy theorem, half mv squared, right? And at this point, if the tension is T, then T minus mg plus a naught that must be equal to mv squared by L. Same as a conventional problem, instead of G you have a G plus a naught. It's like an existing problem in which G is revised to G prime, which is G plus a naught, right? This is all that you need. So this mv squared by r L can be obtained from here and plugged into this, and the tension could be obtained. Simple, right? Let's look at 17. Again, I expected you to have solved 16 independently, right? Alright. So, there is a linear impulse P naught acting at this point, right? The whole thing is hinged about A, so it will rotate about A, right? So, this P naught results in an angular impulse about A. What's the angular impulse about A produced by this linear impulse? P naught into L by 2. In which sense? Anticlockwise sense. In an anticlockwise sense. And what would that do? That will produce an omega. That will produce an angular speed, because angular impulse changes angular velocity. So then this is like I about A into omega minus 0. That's the change in angular momentum, right? Angular impulse will change angular momentum. So I about A, which is 1/3 ml squared into omega, right? 1/3 ml squared into omega. So this omega is known to me from this omega, and this remains constant because it's in a horizontal plane. So until the time it reaches n, this omega maintains constancy. So this rotates with a constant angular speed omega. So the time it takes to go to n, is t1, which is like angular displacement pi by 2 divided by the rate at which it takes place, which is omega, right? From this position to this position, the angular displacement is pi by 2 and it takes place at the rate omega radians per second. So this is the time it takes to go from this position to this position. Fair now? So it arrives at n with an angular speed omega like this, right? Now once it arrives at n with an angular speed in the anticlockwise sense, it's hit by the nail here, which exerts a linear impulse 8 p naught by 3. That means it produces an angular impulse 8 p naught by 3 into, is this L by 2? L by 4. That's a new angular impulse acting on it, and this is clockwise. This is clockwise, right? This is clockwise. Clockwise angular impulse will be change in clockwise angular momentum, final clockwise angular momentum minus initial clockwise angular momentum. final clockwise angular momentum means, let's say, the new angular speed obtained is omega prime. So final clockwise angular momentum is going to be I omega prime. Initial clockwise angular momentum would be minus I omega. So see, it's anti-clockwise. So final clockwise angular momentum minus initial clockwise angular momentum. Final clockwise angular momentum is I omega prime. Initial clockwise angular momentum is minus I omega prime, right? So then this would be I about A, which is 1/3 ml square into final minus initial, which will be omega prime plus omega. So you'll get the new angular speed, and then it will start getting displaced in this direction. So then the time for it to get back to this state is going to be the new angular displacement pi by 2, and that takes place at the rate omega prime, which can be obtained from this, at the rate omega prime, which takes place based on this. So T1 plus T2 is the required time. T1 plus T2 is the required time. Is that fair now? Huh? Clear? Alright. So here we have a system of two blocks connected by a spring originally in its natural state. The whole system resting on a smooth surface, and a mass 1 kg falling from a height 5 meters collides against this, right? And it also had omega equal to 30 radians per second. So while it falls down, descends a height of 5 meters, its omega remains 30 radians per second, because there is no opposing torque to produce an angular acceleration or retardation. Now, just before it hits, it has an impinging velocity root 2 gh, right? Just before it hits this, it has a velocity. So when it hits this mass m, it has a velocity, horizontal velocity v1, which is like root 2 gh 10 so that's 10 meters per second. H is 5, g is 10, so that's 10 meters per second, right? Now, what happens because of this? The collision will cause a change in velocity in the common normal direction. So its velocity component in this direction just after the collision will become E times V1, yes or no? Its vertical component of the velocity will become E times V1 would be its vertical velocity just after collision. So just after collision, its vertical velocity becomes E times V1. E is half, right? Half of 10. 5 meters per second will be its vertical velocity just after collision. Alright. Now, there has been a vertical impulse that has caused a change in linear momentum in the vertical direction for the falling mass, right? There is a vertical impulse acting on this mass. The vertical impulse acting on the falling body must be final linear momentum in the vertical direction minus initial linear momentum in the vertical direction. That's going to be m times Vy minus V1, isn't it? Final linear momentum in the vertical direction minus initial linear momentum in the vertical direction. So Vy minus V1 is this. M is 1 kg. So these many kilogram meters per second. Vy plus V1, which is 5 plus 10, which is 15 kilogram meters per second. Right? That's a vertical impulse. So a vertical impulse is like a normal force acting for a time delta t. A vertical impulse is like a normal force acting for a time delta t. Now, at the instant when this mass hits the block, it has a velocity v1 like this. And because of rotation, see, this guy had an angular speed like this. So this point of contact had a leftward velocity, this point of contact had a leftward velocity. However, the center of mass had no horizontal velocity. had a velocity v1 but had no horizontal velocity. But the point of contact, because of this omega, had a leftward velocity. So then there was a rightward frictional force acting on it. There was a vertical impulse jy acting on this, which was n times delta t, which is n times delta t. So there was a frictional force acting for time delta t, which would be mu n. So there was a frictional impulse which would be mu times n delta t. There would be a frictional impulse acting in the rightward direction, which would be mu times vertical impulse. Mu times vertical impulse would be tangential impulse or frictional impulse, yes or no? Right? So this would be like mu times jy would be the horizontal impulse. Mu times jy would be the horizontal impulse, yes or no? So which turns out to be jx is mu, which is 1/3 into 15, which is 5 kilogram meters per second. Yes or no? Are you all fine with this? Now, the vertical impulse did its job. It changed v1 downwards to ev1 upwards. What did jx do? Jx realized that this fellow had initially no horizontal velocity. When it impinged here, it had no horizontal velocity. Now, a horizontal impulse acted, jx. Jx caused the horizontal velocity to become, let's say, vx. Caused the horizontal velocity to become vx. Now, jx is what? Change in linear momentum in the horizontal direction, mvx minus m0, right? So, which would be m times vx, causing a horizontal velocity to build up on this, causing a horizontal velocity vx to build up on this. So, vx becomes 5 meters per second. This is 1 kg, this is 5. So, 5 meters per second is the horizontal velocity, right? So, then this mass just after the impact had a vertical velocity which is like 5 meters per second and had a horizontal velocity which is 5 meters per second. Clear? Now, this is not the end of the story. This is not the end of the story. At the instant it struck this mass, it had an angular speed omega clockwise, 30 radians per second, right? Now, reckon that it was acted upon by a vertical impulse jy, a horizontal impulse whose line of action passed through this because of friction, jx, right? About the center of mass of this, jy produced no angular impulse, whereas jx produced a anticlockwise angular impulse, So, that caused the change in angular velocity. Let's say original angular velocity was omega. Let's say the final angular velocity became omega f. Clear? Now, what's the angular impulse about the center of mass? Jx into, what's the radius of this? 50 centimeters. So, angular impulse about the center of mass would be jx into half a meter, and that's anticlockwise. So, angular impulse in the anticlockwise sense would be final anticlockwise angular velocity minus initial anticlockwise angular velocity. Final anticlockwise angular velocity would be minus I omega f. I is 2/5 mr squared, right? Minus I omega f is the final anticlockwise angular momentum, change in angular momentum. Final minus initial angular momentum about the center of mass would be minus I omega. Yes or no? So this is the change in anticlockwise angular momentum. And plugging in I equal to 2/5 mr squared and jx equal to 5, we have this opportunity of computing the final angular velocity after the impact. Just after the impact, you now know the vertical velocity, you know the horizontal velocity of the ball, and you also know the omega f of the ball, right? Is that all right? This is the center of mass. So then the ball has a total kinetic energy half m5 squared plus half m5 squared plus half ICM omega f squared is the total kinetic energy, translation plus rotation just after impact of the ball. Clear? Now, so we know everything about the ball before and after collision, right? So the ball side of the story we can close. Now, let's look at the spring block side of the story. Look. Now, just before the impact, what was the horizontal velocity of the ball just before the impact? 0. Just after impact, the horizontal velocity of the ball became 5 meters per second. This is 1 kg. Now, between the ball and the block, was there any external horizontal force acting? For the ball and the block system, for that interaction period delta t, was there any external force acting? No, there was frictional force, but that was mutual, right? So then, between these two in the horizontal direction, the linear momentum must have been preserved. Initial linear momentum of the ball and the block horizontally was 0. So finally it must have been 0. Now this fellow developed a 5 meters per second to the right, and they are of equal masses, so the block must have developed 5 meters per second to the left just after impact, preserving the total linear momentum in the horizontal direction. Clear? So just after impact, this guy develops a velocity just after impact. It develops a velocity 5 meters per second to the left to maintain 0 linear momentum in the horizontal direction. And we could preserve linear momentum horizontally because the only external force acting there was no external force acting horizontally. Friction was there, but that was mutual and internal. Did not produce any net change in linear momentum of the system. Now, are you all okay with this? In the vertical direction, could we have preserved linear momentum for the ball and the block system? Could we have preserved the linear momentum in the see, I preserved linear momentum horizontally for the ball and the block, and I got the block moving leftwards with a velocity 5 meters per second. In the vertical direction, can I do the same? No. Why? There was gravity and there is also normal reaction acting, right? So there is external force, the system is subject to external force, and in the vertical direction, we cannot preserve linear momentum of the system. Now, once I understand this, the block, this guy then undertakes a parabolic trajectory, right? This fellow, the ball, just after impact, it moves with omega f, and it undertakes a parabolic trajectory. Horizontal velocity 5 meters per second, vertical velocity 5 meters per second. This remains constant, this changes with time. And what happens to omega f? It remains the same, right? So at the highest point, it still has omega f and it has 5 meters per second, the vertical gets low. So this is the story of the ball just after the impact, and you know the trajectory is going to be parabolic, maintaining omega f constant and Vx constant for the ball, right? Now for the block, this is 5 meters per second. Oh, okay, 2 kg. Now, for maximum compression of the spring, what must happen? Relative velocity must be 0, or both blocks must have the same velocity. So you could solve this problem in the center of mass frame like I did in the last class, or you could even solve it from the ground frame. So in the ground frame, since I already solved this in the center of mass frame, in the ground frame it's as simple as this. At the instant of maximum compression, both acquire the same velocity with respect to the ground, and this becomes x max. They preserve the same linear momentum. They started with a linear momentum of 1 into 5, and at the instant of maximum compression it became 1 into v plus 2 into v, that is 3 into v. So the common velocity becomes 5 by 3 meters per second, right? And where does it all come from? The original energy was half of 1 into 5 squared. It got converted into half of 3 into v squared plus half k x max squared. That's energy compliance. That's energy compliance. Half k x max squared. So x max could be computed, or like I did in the last class, the center of mass frame reference also, reduce mass and stuff, you could have done it. I'm sorry, k x max square, I'm so sorry. And you can realize that there is loss of energy in this collision because it's an inelastic collision. E is not 1. So that's why the final energy is going to be less than the initial energy. The final energy would be energy in the ball plus kinetic energy of the block, half of 1 into 5 squared. And that must have been less than the energy with which it struck the block, right? In fact, it struck the block with a total energy mgh plus half I omega square. That's what it had. So I am not doing those calculations, the idea is simple. Alright, so we have a ring of radius r and mass m on a frictionless surface, and there is a particle of mass, say mass small m, originally at a time t equal to 0, it's at a, and it starts to fall, and after a while, with respect to the ring, it reaches B. With respect to the ring, it reaches B, describing an angle theta as perceived by an observer on the ring, right? Now, we'll look into the physics of what happens in a situation of this kind. One thing for sure, as far as the ring plus particle is concerned, as far as the ring plus particle, call this the x direction. Call it the x direction. As far as the ring plus the particle is concerned, in the x direction, is there any external force acting on the system? This is our system. Ring plus particle. Is there any external force, net external force in the x direction? No. Again, because there is no friction, so there is no force in the x direction acting, right? No external force acting in the x direction on the system. So Fx is 0 on the system. For the system, force in the x direction is 0. That means if the force in the x direction is 0, for sure the linear momentum of the particle plus system in the x direction must be preserved. The total linear momentum in the x direction for the system must remain constant, right? So the linear momentum in the x direction must be constant. Hey, but originally the system started with 0 linear momentum in the x direction. So it will maintain 0 linear momentum in the x direction always? Yes or no? Right? This constant is 0. Clear? Now, while this particle descends downwards, it develops a rightward velocity. It develops a rightward velocity. As seen by a ground observer, it will develop a rightward velocity. So then this particle will present a rightward linear momentum to the system. To counter that rightward linear momentum for the system, the ring must acquire a leftward velocity v so that the net linear momentum in the x direction remains. Yes or no? So then the ring on its part, by the time this particle reaches B, the ring develops, let's say, a velocity v to the left. The ring develops a velocity v to the left. Clear? Now, if there is an observer at the center of the ring, integral with the ring. If there is an observer at the center of the ring, attached to the ring, what would be the motion of this particle that this observer perceives? Circular. The motion of this particle as perceived by an observer at O attached to the ring will be circular, right? So the trajectory of the particle, however, the trajectory of the particle as seen by a ground observer will not be a circle, because there will be a combination of this motion plus the motion that it has common with the ring, combination of, right? So not with respect to the ground observer, but with respect to an observer here, the motion of this particle will be along this circle. Are you okay with this? Huh? Which means, let's say u is the velocity. Let's say u is the velocity of the particle at this instant as seen by the ring observer, and it will always be along the tangent to the ring, because this will be the trajectory. The velocity with respect to this will always be along the trajectory with respect to this particle. The trajectory with respect to this particle is circular, so the velocity will be along the tangent to the ring, Is that all right? Now, the velocity of the observer is v leftward, u is the relative velocity of particle as seen by the ring observer. As seen by the ring observer, this is the relative velocity of the particle. Which is u naught. This is the velocity of the observer. The velocity of the observer is v. That means if I add vectorially this v and u, this will be the total velocity of the particle as seen by the ground observer. The velocity of the observer plus the relative velocity of the particle will give me the absolute velocity of the particle. Right? So a vector sum of v and u will give me the absolute velocity of the particle. Velocity of the particle in the ground frame of reference. Is that okay so far? Now, this is the radius. It makes an angle theta with the horizontal. So the tangent will make an angle theta with the vertical. So the tangent will make an angle theta with the vertical. Clear? So angle between v and u is 90 plus theta. And the vector sum of these two will give me the absolute velocity with respect to the ground. Now, the linear momentum of the ring in this direction must be equal to the linear momentum of the particle in this direction, so that there is no net linear momentum housed by the system, right? Which means the linear momentum of the ring in this direction is m into v, and the linear momentum, and all this is by a ground observer. I am preserving this linear momentum in the ground frame. So at this instant B, between A and B, I am preserving linear momentum. And for the particle in the rightward direction, it's like u sin theta minus v. See, the net velocity in this direction for the particle will be u sin theta relative, the relative velocity in this direction plus velocity of observer in this direction will give me absolute velocity in this direction, which would be u sine theta minus v will be the velocity of the particle in this direction as seen by the ground of the observer. So that's going to be m into u sine theta minus v. Is that all right? Clear? So we have like 2v is u sine theta. Theta is 30 degrees, so half. So u is 4 times v. That's one equation. That's one equation between u and the relative velocity v, relative velocity u and the velocity of the ring, absolute velocity of the ring. Now, the displacement of the ring, displacement of the ring. One thing for sure, if the linear momentum in the x direction is constant, right? That means the center of mass of the ring plus particle, center of mass of the ring plus particle has the same velocity all the time, right? But initial velocity is 0 of the center of mass of the ring plus particle, so it remains 0 all the time. That means the x coordinate of the center of mass of the system will be the same. This moves here, this moves there. They move in a manner that the x coordinate of the center of mass, x coordinate of the center of mass of the ring plus the particle must be the same. Must be the same. Are you okay with this? Okay. When the particle goes, so now we will, like we did the raft, look at the raft, we'll look at superimposing the motion of the particle first and then the raft going on to restore. The raft will go on to restore the x coordinate. So by what amount does the particle disturb the numerator of the x coordinate of the center of mass? The particle disturbs it by an amount, this, because in its journey from A to B, this is its displacement in the x direction. This is its displacement in the x direction. And if I choose this as the positive x direction, then the disturbance to the numerator mixi that it causes is m into this length, m into this length, right? That's the disturbance with a minus sign because it's in the negative x direction. So the disturbance, change in mixi caused by the particle going from A to B is m into this length. This length, see, this is r, say, so this length is r cos theta. So AT would be r minus r cos theta. So minus m into r minus r cos theta. That's the change in mixi caused by this particle. What does the ring do in its turn? The ring, now let's say the particle comes and stops here. The ring now moves by x units to the left. The ring along with the particle moves by x units to the left. So then the change that the ring plus the particle will produce to maintain the x coordinate of the center of mass is m plus m into the ring moving by x units to the left, and this must be 0. This is the change in mixi caused by motion of the particle, and then the particle stopping here, and this is the change in mixi caused to the numerator by the ring accommodating and nullifying that change. So the net change in summation mixi must be 0 to preserve the x coordinate of the center of mass. So this will give you the distance moved by the ring leftwards. This will give you the distance moved by the ring leftwards to preserve the center of mass of the ring plus particle. Is that all right? No issues? Now, when the particle arrives at B, it has a certain velocity as seen by the ground observer at B, in the ground frame, the velocity of the particle at B, this is the velocity of the particle at B, this is the velocity of the particle at B, that's going to be given by Vb squared is the resultant of the velocity of the observer plus the relative velocity u. So it's going to be v squared plus u squared plus 2uv cos 90 plus theta. Angle between u and v is 90 plus theta. That will give me the velocity at B. That will give me the velocity at B. Clear? Absolute velocity, velocity in the ground frame. So this is like you can write everything in terms of u or in terms of v based on what you want, u equal to 4v. But then the important thing is you would know it in terms of one of the two things, minus 2uv sine theta. Minus 2uv. So you know Vb? You know Vb? You can plug in v equal to 4u or rather u equal to 4v and arrive at Vb in terms of the velocity, absolute velocity of the ring, right? And now between A and B, I can apply work energy theorem. I can apply work energy theorem, right? In fact, loss in potential energy because of loss of altitude of the particle must be gain in kinetic energy of the ring plus gain in kinetic energy of the particle, right? So then between A and B, loss of potential energy is mg into this length, mg into this length, r sine theta, that's the loss of potential energy. And that must be gain in kinetic energy of the ring, half mv squared plus gain in kinetic energy of the particle, half m vb squared, half m vb squared, etc. That's energy compliance. That's energy compliance for the system. And then Vb you can plug in terms of u or v and solve for v. Solve for v, right? From this equation you can solve for v, the velocity of the ring at an instant the particle reaches b. Is that all right with all of you? Right? So this is the complete physics of the problem. And then you can just solve for these various entities here. Clear? So we have this system, this framework in which a block with the masses, springs, pulleys connected as shown, and this framework has an acceleration 4 meters per second squared in the x direction and a vertical acceleration 4 meters per second squared. Now, there is friction between the masses and the bigger block, between masses A and B and the bigger block. Coefficient of friction is mu. And we want to be able to find mu so that the spring remains unstretched all the time. Under the influence of whatever is happening here, the spring remains unstretched. Such is the value of mu that we want to find. Now, one thing for sure, if mu is very large, right, then there would, no matter what, there would be no relative motion between this M and this M and this block, right? And the spring will remain unstretched, right? If you lower the values of mu, there would be greater possibility for the two masses, for the mass and the block to slide with respect to each other, and there would be a greater possibility for the spring to get stretched. So that means you can't go below a certain value of mu, you can't go below a certain value of mu to accomplish an unstretched spring, right? So there is a minimum mu in place, there is a minimum mu which you require, there is a minimum mu that you require so that the spring remains unstretched, Now, that minimum mu must be a state where it's precariously holding on to these masses, to the mass M and the block, the mass M. That means the normal reaction between A and B is such, A and the block is such that the force of friction between M and the block just about reaches maximum static. So the minimum value of mu would be that, which would just about bring a maximum static friction between A and the block, which would just about bring maximum static friction between A and the block. A value of mu smaller than that will cause the force acting on this to be larger than the maximum static friction and will cause the spring to get stretched. A value of mu greater than that will cause maximum static friction to be greater and to prevent any further sliding. So the value of mu that we are seeking is 1. The value of mu that we are seeking is 1, in which the force of friction between A and the block is just about maximum static. Is that all right? That's the value of mu that we are trying to find here. Now, we will solve this problem. We will solve this problem in a frame of reference attached to this. That means in a non-inertial frame. In a non-inertial frame, we will have to account for pseudo forces. In this case, there would be a pseudo force in the x direction. There would be a pseudo force in the y direction, because there are components of acceleration in both these directions, right? So then, in the frame of reference attached to this, let's draw the free body diagrams of A and B. Let's draw the free body diagrams of A and B, in which the spring is unstretched, right? And the masses are being acted upon by a limiting friction, maximum static friction, for the proposed value of mu. Clear? So for A, for example, A. This is our frame of reference. In this frame of reference, there would be a tension T. Now, there would be a pseudo force MAX like this. That means 2 into 4, 8 newtons of pseudo force acting leftward, right? Eight newtons of pseudo force acting leftwards. No spring force. Now, there is 4 meters per second squared upwards. That means 8 newtons of pseudo force acting downwards. There is 20 newtons of weight acting downwards. With respect to this frame, there is, in the ground frame, there is acceleration of this mass m. But in this frame, the acceleration of mass m in this direction is 0. So in this direction, in this frame, there is no acceleration. Of the mass m in this direction. So the normal reaction R must be 28 newtons. Yes or no? Frictional force, since this has a tendency to slide to the right, frictional force on it would act leftwards, and we are trying to find that value of mu for which frictional force has reached its maximum permissible value. That means mu times R, leftwards would be the frictional force. That means 28 mu will be the frictional force. Mu newtons would be the frictional force. Right? Now again, the spring is remaining unstretched. So in this frame, this mass m has no acceleration, this mass m has no acceleration in this frame. That means net of all forces in this direction on this mass as seen in this frame of reference must be 0, right? That means G must be 8 plus 28 mu, T must be 8 plus 28 mu, clear? Tell me, are you all fine with this so far? Let's carry out a similar thing for this mass m. Let's carry out the T, of course, you realize is the tension in the spring at this instant. For this block B, for this block, $20 newtons downwards, weight, it's in a frame of reference 4 meters per second squared upwards, so there would be 8 newtons downwards, pseudo force. And then the frame has 4 meters per second squared rightwards, so there is 8 newtons of pseudo force in this direction. Right? There is normal reaction from this. Realize that in this frame of reference, this has no acceleration with respect to this. So the net force in this frame of reference on this mass in this direction must be 0. So there is an 8 Newton force which is pressing B against this. So the reaction R prime must be 8 newtons to the right. Reaction R prime must be 8 newtons to the right. Is that all right? Okay. Now, it has a tendency to slide down. Maximum static friction will act upwards. That means mu times 8. Mu times 8 will act upwards. And then, of course, there is tension T acting upwards. Yes. So now, again, in this frame of reference, this M has no acceleration because the spring is unstretched, the masses are staying put, right? So no acceleration in this direction. So that means net of all forces in this direction in this frame of reference must be 0, real plus 0. So that means we must have T plus 8 mu equal to 28. T plus 8 mu equal to 28. So equation 1, equation 2, we don't need T. So plug in T equal to 8 plus 28 mu. So 8 plus 36 mu equal to 28, mu equal to 20 by 36, which is 5 by 9. Mu is 5 by 9. So this is the minimum mu. The more the merrier. If the value of mu is larger, then anyways it will remain unstretched. If the mu is smaller than this, then the spring will get stretched, right? So this is the threshold mu. This is the threshold mu. Values of mu larger than this will cause the spring to remain put. Values of mu smaller than this will cause the spring to elongate. Clear? Now, once we understand this, the next part of the problem is, if mu is reduced to 9 by 35th of its value, that means the new mu is 9 by 35 of this, then obviously the spring will get elongated. The spring will then get elongated because friction won't be enough to prevent that elongation, right? So, calculate the maximum extension of the spring. Calculate the maximum extension of the spring under such a situation. So then, if the new mu, call it mu prime, which is 9 by 35 of 5 by 9, which is 1 by 7, which is 1 by 7. That's mu prime. We want to be able to compute the maximum elongation in the spring. Okay. Again, one thing, everything measured in this frame of reference, right? We'll apply work energy theorem in this frame of reference. Alright. In this frame of reference, we'll apply work energy theorem with the revised. One thing for sure, that in this frame, as long as the velocity of this is larger than the velocity of this, right, the spring will get elongated. That means relative velocity of this in this frame is greater than 0 will cause the spring to elongate. The moment the relative velocity of these masses will become the same as the velocity of the frame, the spring will seek no further elongation. Are you okay with this? No? I'll repeat. Okay. Why is the spring getting elongated? Look at this observer on this frame. On this frame, look at this observer. This observer finds this mass to have a velocity to the right. But the velocity of this mass as seen by this observer is what? Relative velocity of this mass in this frame. So if the relative velocity of this mass in this frame is to the right, the spring will get elongated, right? Down the line, if this keeps getting retarded under the influence of friction, spring force and other things, the velocity of this in this frame becomes 0. That means this guy finds that this continuously gets retarded because the spring elongates, this will retard, eventually this guy will observe that the velocity of this becomes 0, but the velocity of this as seen in this frame is a relative velocity. So when the relative velocity of this becomes 0 in this frame of reference, the spring would have sought its maximum elongation. When the relative velocity of this mass in this frame becomes 0, then the spring would have reached its maximum elongation. Are you okay with this? So, in a state of maximum elongation, the kinetic energy of this and this in this frame of reference is 0. In the original state where we started, this had 0 velocity in this frame, this had 0 velocity in this frame. So kinetic energy of this in this frame and kinetic energy of this in this frame is 0. So in the initial state, the kinetic energy of A and B in this frame of reference is 0. In the maximum elongated state, the kinetic energy of A and B in this frame is 0. So in this frame, the change in kinetic energy up to a state of maximum elongation is, is 0. Is that all right with you or not? Because in work energy we will require change in kinetic energy in this frame. So change in kinetic energy in this frame up to a state of maximum elongation is. Now let's go on to apply work energy theorem, given that the spring receives a maximum elongation of x max. So now we will look at a system comprising M and the string and this M as one system, and we'll apply work energy theorem on this system up to a state of, from the initial state up to a state of maximum elongation in this frame of reference, Clear? Look, first of all, there is a spring force acting on this. Work done by the spring force would be negative of the change in elastic potential energy of the spring. Work done by the spring force is going to be negative of the change in elastic potential energy of the spring, which is minus half k x max squared. Minus half k x max squared is the work done by the spring force, right? Now, instead of mu here, we'll have mu prime. Instead of mu, we'll have mu prime. Now, this mass moves to the right by an amount x max in this frame of reference. So, the work done by these two forces is going to be 8 plus 28 mu with a minus sign into x max. Work done by these two forces, the point of application of these two forces will move like a x max to the right. So, the work done by these two forces would be negative. So, minus, instead of mu you will have mu prime, instead of mu you will have mu prime, that's the only difference. So, minus 8 plus 28 mu prime into x max, that's the work done by these forces. And then on this mass end, if this has moved x max to the right with respect to this point, then this must have moved x max downwards with respect to this point, because this string length is constant anyways, right? So then, for this mass m, we have 8 plus 20, which is 28 into x max is the work done by gravity plus pseudo force, and then there is negative work done by this friction. So, minus 8 mu x max, mu ki jagah mu prime, where mu prime we've computed is 1 by 7, x max. This is the work done by all forces. Is that alright? And this must be, and this is the work done in this frame of reference, and this must be change in kinetic energy in this frame of reference, which is 0. In this frame of reference, change in kinetic energy must be 0. And this gives us the opportunity to compute x max, the maximum elongation. Clear? Alright, so we have a situation here where 3 insects follow a complicated trajectory A, B and C. Initially at the vertices of an equilateral triangle of side L, the 3 insects A, B and C follow a complicated trajectory but with constant speed, such that at any given instant of time, the direction of the velocity of A points towards where B is, the direction of the velocity of B points towards wherever C is, the direction of the velocity of C points towards wherever A is. This is at t equal to 0. Now, no matter how complicated the trajectory is, from symmetry what really happens is, at any given instant of time, the 3 particles, the 3 insects A, B and C will remain at the vertices of an equilateral triangle. From symmetry we can say that they will remain at the vertices of an equilateral triangle at all times. It's another issue that the side of this triangle continuously decreases, because each particle is approaching the other one, so the relative separation between the two will decrease, right? So it's the positions of the 3 particles will always be the vertices of a decreasing equilateral triangle. Now, not only is the side of the equilateral triangle decreasing, the orientation of the equilateral triangle is also changing, right? Because if A is here, it would go somewhere there, B would go somewhere here, C would go somewhere here. It would be a decreasing equilateral triangle which would be reorienting itself in space. Yes or no? Right? Now, no matter how it's reorienting itself, for sure, at any given instant of time, they remain at the vertices of a triangle which is equilateral, and now R. Eventually, at time t equal to 0, R is L. In a time in which they converge, R becomes 0. When R becomes 0, that means the side of the equilateral triangle would have become 0 and the 3 insects would have then met. So R runs from L to 0 progressively, causing the side of the equilateral triangle to diminish. Fine. Now, realize that R decreases with time. R decreases with time. So, dr dt is less than 0. Because R is decreasing with time, dr dt is less than 0. Magnitude of dr dt is a measure of their relative, let's say, if you look at A and B, the magnitude of dr dt will give me their relative velocities along AB, will give me the relative velocity of A with respect to B along AB, yes or no? Are you there with me? Mod dr dt will give me the relative velocities of A and B along AB, right? Relative velocity along AB will measure how fast R is decreasing with time, yes or no? The relative velocities along AB will measure how fast R is decreasing with time, that is mod dr dt, right? Now, at this instant, A has a velocity v like this and B has a velocity v like this. This is 60 degrees. Now, what is the relative velocity along AB? Velocity of A along AB minus velocity of B along AB. Velocity of A along AB is v. Velocity of B along AB is minus v cos 60 degrees. So, relative velocity along AB is 3v by 2. Relative velocity along AB is v minus v by 2, that is 3v by 2 is the relative velocity along AB, and that's mod dr dt. That's mod dr dt, yes or no? Hey, but dr dt is negative, so mod dr dt would be minus dr dt, so minus dr is 3v by 2 dt. Yes or no? Integrate both sides. At time t equal to 0, R was L. At time t equal to tau, R became 0. Right? So that gives me like a 3v by 2 into tau equals L, or tau equals 2L by 3v. In this time, they meet. Now, after how long would the separation become L by 2? Same thing, all that you need to do is, at time t equal to 0, R is L. At time t equal to tau 1, R is L by 2. If this becomes L by 2, you will get tau in which the separation becomes L by 2. That's the next part of the problem. Yes or no? But this is a fundamental. Just by suitably applying the limits, you know the time in which the separation becomes 0, becomes L by 2, becomes L by 3, becomes L by 4, and so on and so forth. Clear? Are you fine with this? Now, the last part of the problem, which says, find the equation of the trajectory of one insect with respect to another in a polar system, the r theta system. I'll explain this. Let's say I want to find the trajectory of B as seen by A, where R is the instantaneous separation between A and B, and theta is a measure of the orientation of AB. Orientation of AB is changing with time? Yes or no? R, I want to find the trajectory of B as seen by A. Where R is the instantaneous separation between A and B, and theta is a measure of the orientation of AB with respect to a certain AB. Alright. What we do is, let's say this was the original AB. This was the original AB, right? Let me call this a reference line for measurement of angle for theta. And since I'm talking of the trajectory of B as seen by A, it's as if A is pinned at a point and B is assuming a certain, it's as if A is here and B is undergoing a certain trajectory, right? After a while, B was originally here, let's say B was originally here, the separation was L, and now after a while, let's say B comes down to this point, and AB is R. So I want to be able to connect R and theta. I want to be able to connect R and theta, which is the trajectory of B as seen by A, right? Now, one thing for sure, at any given from the ground frame, the velocity of A is V like this, the velocity of B is V like this, right? Absolute velocities. But the earlier equation that we wrote, which was like dr equal to minus 3v by 2 dt, will still hold good because r is changing at this rate. 3v by 2 dt in a small time dt, this is what happens, right? The change in r in a small time dt is minus 3v by 2 into dt, which is just the earlier equation. That's measuring how r changes with time. There is an angular velocity of B as seen by A. There is an angular velocity of B as seen by A that will measure d theta dt. Isn't it? D theta dt would be the angular velocity of B as perceived by A. Is that all right? Huh? The angular velocity of B as perceived by A will be d theta dt, right? And what will cause d theta dt? This is A, this is B. The velocity of B could be resolved as V sine 30 degrees, sine 60 degrees perpendicular to AB and V cos 60 degrees along AB, and this is B. Hey, do you realize that their relative velocity perpendicular to AB will be a measure of omega of B as seen by A? Yes or no? So then this omega would be the relative velocity perpendicular to AB divided by the length r? Yes or no? So that's going to be V root 3 by 2 divided by the corresponding length r. That will be a measure of omega. The perpendicular relative velocity perpendicular to AB divided by the length AB will be a measure of omega. Yes or no? No? So d theta dt is actually V root 3 by 2r. Clear? So we have like r d theta as V root 3 by 2 dt. R d theta as V root 3 by 2 dt. We need to connect r and theta from equations 1 and 2. What would we do? Divide one by the other, dt goes into oblivion, r and theta come for action. Divide 1 by 2, dt goes away, divide, so we have like 1 by r, dr d theta when I divide 1 by 2 is like minus root 3, is minus root 3, yes or no? Or dr by r is minus root 3 d theta, integrate both sides. The original AB was theta equal to 0. We call the original AB as the reference for measurement of theta. So the original AB was theta equal to 0 when r was L. When r was L, then that theta was referred to as theta equal to 0, the original position configuration of AB. And then eventually when theta becomes theta, separation between B becomes R. So this R and theta is with respect to A, right? So we have like a log R by L equals minus root 3 theta, or R equals L e power minus root 3 theta. Right? This will give you the trajectory of B as seen by A. Got me?